I'm gonna start the recording and let's get started. So we're gonna start today with an introduction to statistics, research, and design. And we talked. I think really does like me. Okay. So last time we talked already about the different tasks, the different mainstays of statistics. Today we're going to talk about again, but only to set the stage to dig a little deeper into things. So basically last time we discussed, we have descriptive statistics and we have inferential statistics. Thirdly, we have research methodology and research design as a third, not listed here, task of statistics. But let's quickly start with descriptive statistics. So when you have statistics, when you have data, you have data on different levels. So you could have one entry, one data row in Excel for each individual, for each subject of your population of interest. So obviously, if you want to communicate now something about this data to a broader audience, so you want to communicate it to your peers, to your colleagues, to your professors, to your boss, to the world, you want to write a scientific article, you need to find a way to kind of make this more digestible. And the way to to make it more digestible is to use descriptive statistics. And so you organize, summarize in order to be able to communicate groups of numerical information. So basically you find ways to use matrices that characterize your data in a shape or form that you can communicate them to others. Inferential statistics is a little bit more specific in that regard. It's not only communicating characteristics. Inferential statistics you also use to draw inferences, to gain insights, to draw conclusions based on either differences between populations, dynamics within populations, or whatever you're essentially interested in, associations, differences, you name it. So you make estimates within your sample population, and you're trying to gain these estimates for it to be generalizable to a larger population. So lastly, and so the third point is the design of studies, design of research, where you basically mean to give a statistician, and it's important that a statistician has a seat at the table when it comes to designing studies, because it comes down to questions like how often do you need to collect data? How do you need to study individual to get valid and useful data? How many individuals do I need to study to really can be able to make a solid estimate that I can then use for interpretation of my data? So for these things, the design of research is definitely another mainstay and another task of statistics. So in essence, what you do in terms of definitions, you define populations. And your population is basically a collection of individuals within a defined group of people. So this can be the world population, that can be the population of the US, that can be the population in New York City, for example. So it's a definition that is defined in your research. So now the problem is that you cannot study each and every member of a large population. So if you want to study the world population or the US population, this is extremely difficult. Therefore, you're trying to find a subset of your population that is representative and generalizable to your overall population. So you're doing this with a technique that is called sampling, and we will talk about this in chapter 5, where we basically will look into different approaches in sampling. And unfortunately, this is one of the big problems that research generally has, that samples that are generalizable to overall populations are very hard to find. And so basically you have experimental studies and you have observational studies. So experimental studies are studies where you study an intervention. So you study some form of intervention, be it the blood pressure medication or whatsoever, and we talk about a couple of them later on in this class. Whereas observational studies just mean to observe something within a population. And this being said, when it comes to population in the US, you have the overall population, which is quantified once every 10 years with the US Census, which is one of the largest censuses in the world. When it comes to samples that are generalizable, there's one of the largest nutrition and health studies, the ENHANCE study, conducted in the US from the CDC, which is essentially aiming to exactly do that. They're studying in a very sophisticated design observationally data from collectives in the US in a certain shape or form that they can actually use statistical methods to extrapolate their finding to the US population. And that's actually a very elegant design, and it's a study that is for an epidemiologist like really a pleasure to analyze. So it's a wonderful study, wonderful example to actually how you can study a sample and understand the population. It's the most representative studies of the study of the US essentially, and really allowed for a lot of insight over the last 20, almost 30 years, I believe the study is ongoing. That this is really a wonderful contribution to science. So this is basically population and sample. So, but basically what you try to do with a sample, you try to understand the population by creating such a representative sample, including observing and just looking at different data that you're collecting without doing anything, and also to use them for an experimental study where you're actually placing an intervention, and then with replication, you do the same study repeatedly. And if you find the same dynamic, you can extrapolate your findings in your sample to the population, and you can conclude, okay, that blood pressure medication that I'm using on that sample, and that sample will most likely also work with my population. If I give people that need blood pressure medication, it will react in the same way and fashion in my population. So that's the idea of a sample. Any questions on this? If not, then we can actually go deeper. So the most important thing with statistics and the most important thing in research is really data. And data is in principle categorized in two main groups. These two groups are basically discrete and continuous data. Discrete data are basically variables that can only take on specific values. They're subcategorized into nominal and ordinal variables. Continuous data are variables that can take on a full range of value and can be subcategorized into interval and ratio variables. What does this mean? So you basically, So when you think of nominal data, you basically think of a category within which you categorize each individual that you have collected data from. If you have ordinal data, you have a ranking of data. So what could be a category B, for example? It could be, I don't know, it could be biological sex. It could be race, ethnicity, religious affiliation, married, non-married, you name it. It's really everything that categorizes an individual in one respective group. And that grouping, that's a nominal variable. If you have this assigned to each individual, then you can basically transform this discrete data to interval data where you're basically counting each individual in that group. But basically the category per se is called a nominal variable. If you have an ordinal variable, you have a ranking of data. That means, let's say you want to quantify the happiness in a population and you have a survey that allows an individual to categorize their own level of happiness into 5 different categories, from very happy to not happy at all. So you basically, this individual is self-reporting the data, and then you get one category for each individual. The 5 categories we have, that's the ordinal variable. The assignment to each group, that becomes then something that can be transformed to an interval variable. Yes.
Would it still be ordinal data if it was a scale of 1 to 5 for happiness, or only if it's the terms?
Well, 1 to 5 would be, it is, see, that's a very good question, because essentially it is an ordinal variable because it follows an order. So whatever you label it, and you will see actually, so there's actually a really cool quiz question in one of the practice quizzes. You will see this with the size of a bed. So you have like, the smallest bed would be like a single, then you have double, then you have queen, then you have king, then you have California. And the actual categorization in these different sizes of bed are basically, that's the ordinal variable. The assignment to each group and then the quantification of how many California beds and how many king beds were sold in 2020, that's actually a continuous variable. And that is really where the important distinction is to be found. Because when we come to continuous data, we have two different data forms. We have two subcategories. We have interval data. These are numbers that are equally spaced, can always be negative. A ratio data, that's a count, where it basically has a meaningful zero. And the most wonderful example to categorize that is basically thinking of cookies. You have nominal variable, that would be the name of the cookie, whether it's chocolate chip, oatmeal raisin, whatsoever, whatever cookie you want. Then you have an ordinal variable, that's the ranking of your favorite cookie. How do you like those cookies on a scale to from 1 to 10? That's your ordinal variable. An interval variable would be, for example, the temperature of the cookie. Is it out of the freezer? Has it been on the counter? Or is it something that I just warmed up in the stove? That is the interval variable. Another ratio variable is the count of the cookies. How many cookies do I have left? Do I have 10, 5, or none, which is 0? That's the meaningful 0. Yeah. So now let's go to that first. Okay, may I ask somebody of you to volunteer? Yeah, all right, thank you. So quick, simple task. I want you now on the following slide to look at those 4 words that are written and say each of those words as quickly as you can. Super. Okay, very good. Now look at the word and tell me the color of the font. You ready?
Green, blue, red.
Yeah, that was pretty good. Kudos, respect. So what this is the so-called Stroop test. So you have just seen a very good presentation of how to do it very fast. But in clinical diagnosis, and I'm not a psychologist, I'm not an expert on this, but that's what I have read up on it. So in clinical diagnosis, this can be used to diagnose brain pathologies. So somebody with dementia, somebody who had a stroke, somebody who has some certain congenital deficiencies will have a hard time dissociating these two components, word from color. So the time between quote unquote congruent, where you have only one color and you're just reading the word, versus stating that color, which comes from a different center of the brain, these times will be substantially different. So if you read up on it, the Stroop test is the name of the test. So I'm not going to speak more about it because I'm not qualified to speak about it. But essentially, you want to see how long does it take what's congruent and compare it to when it's in a congruent measurement phase. So this being said, we have now a little bit of an exercise with that. And this really looks like me. Okay, we have a little exercise, and this is the Excel spreadsheet that I've shared with you. So we have here the data of 24 individuals. So we have here an ordinal data, which is the ID, which is basically the chronological sequence that individual did the assessment. Then we have here congruent. Congruent meaning it's one color, it's just reading the words. fast, simple. And if you look at the times, they're also quite lower than compared to incongruent, where basically you were asked to state the color of the font with a different meaning written on the slide. So what we see here are two different variables. And as we know, it's time, but it's basically, this is actually our ratio variable, right? So it's basically, it's a count. It has a meaning for 0. So what you would be looking at is here a data set that now in the first step, you would like to kind of characterize. And one way to characterize this, and this is really the exercise, right? It's like why I have implemented this exercise is to give you a possibility to kind of take baby steps in Excel. And so the idea is really to kind of use functions to describe this data. And I work here under the assumption that you all know from high school an arithmetic mean, which is basically the sum of all individual entries divided by the number of entries. So we have 24 entries, and we take the sum of all these seconds that have been used to complete the task, and we're dividing that by 24. Alternatively, we can use an Excel function, which is here the so-called average function. So I believe we've talked about the average already last class. So average, you indicate with an equal sign that now a function is about to start. Then you have the function average, you open a parenthesis, and then you have B2 to B25 is marking here that selected range from B2 to B25. Simple, right? And that gives you a congruent average of 14 seconds. So now if we want to do the same for incongruent, one simple way to do that, if you have a setting like that, where you have as many entries for congruent and incongruent is right next to it, you just click on the one formula for congruent, which is our average from B2 to B25. You go on the right lower corner and you're clicking on it and you're pulling it to the right, will give you automatically the average of C2 to C25. So this being said, this is a way how you can describe your data. And this is a very simple way to do that. If you would want to rank this data, so here we have the chronological sequence individually came in, right? Another way to look at this is like, I actually want to know who was fastest, who was slowest. So I do this now for this example by pressing Command C and copying this in a new spreadsheet. So down here, I open a new spreadsheet and I just copy this here in column A. And once I have both columns selected like that, I just have to go on data. So here in the tabs, I go on data, I click on sort. And here I need to make sure that sort, it activated my list as headers. Then I click on column. I click on congruent, smallest to largest, and then I press OK. Then it will automatically sort from the smallest to the highest, and this will essentially be sorted in according to the magnitude of the time passed. If I now want to rank this, I can do this easily by just labeling the column with rank. And now I just sort it 1, 2, 3. I select 1, 2, 3. I go to the right lower corner. Again, where the cursor changes and I pull this all the way down, it sorts it according to the magnitude of time passed or time needed to complete the task. If I want to sort it back, and that's the beauty of it, I go on sort. Again, my list as headers needs to be clicked. I click on ID, it's going to sort it backward. So it's going to do it again, sorting it as per the chronological order the assessment was done. And it attached now the respective rank to the individual. And that is important to understand when you deal with data. You need to align it and you need to treat it as the matrix it is. Good. So that's one way to do it. Another way to do it, maybe let's look at the slide first. So this is how you treat data, and this is how you transform data in an ordinal variable, for example, which would be the rank, right? Rank is the ordinal variable. The actual ranking is then becoming the ranking within the group. So, but you cannot use this data to essentially do any arithmetic. So that rank is not something you could work with. So this is where it becomes a discrete data point. So now when you think of data, you have nominal, ordinal, interval, and ratio. So now when we have ratio, as we have in our Stroop test, you could hypothetically also make it discrete. And that's the beauty of it. Why would you make it discrete? Because hypothetically, you may be interested to know how many individuals took longer than 15 seconds to complete the task, right? And you can easily do that in Excel. And this is took longer than 15 seconds. And the beauty of that is that Excel has functions. So this is a little bit more of a complicated function now, but go with me and try to follow along with the logic. So you say equal sign, and you say if parentheses open, if my data congruent is greater than 15, comma, what am I supposed to do then? Then I make a 1, comma, what else? If it is not greater than 15, then give me a 0. If you do that, you essentially can complete this formula all the way down, and it will give you a 1 for each entry that is greater than 15. So you have here 1 for each entry that is greater than 15. Why is that useful? Because if I want to understand now a number of entries greater than 15 seconds, is sum of D2 to D25. So now I know that 9 individuals took longer than 15 seconds to complete the task. Now let's modify this a little more. So we have now 15. 15 is now a number, right? So if I say here 15, and I'm replacing now the 15 here with I2, no, G2, I can do something which we in programming call soft coding. Soft coding means that it uses whatever function I use, it takes actually the criterion or whatever determining factor from somewhere else, and I don't write it in my formula. That's soft coding. If I write it in there like I wrote it in before and I write 15 in the formula, then I'm hard coding it. Generally, those of you that are inclined to go into computer science or programming or statistics, distinguish those two and favor soft coding always, because it will make your life easier. Good. Okay, so if I do that, the formula will result in the same thing, same result. If I would like to complete this formula now all the way down, if I would do that just by pulling it down here, it would basically shift this G from G2 to G6. Therefore, I need to lock this cell in. I need to say, okay, so this is the reference cell. Irrespective of which row you're in, always use that particular value, and you do that with the $sign. So you say $G, $2. I know this is now all a little much, but follow along, look at the code again. It will make your life easier to know that. So if you lock it in and now you're completing it all the way down, you will always reference the 15, G2. And what's the beauty of that now? And this is the advantage of soft coding over hard coding. If I'm changing now that reference cell, it will automatically change all the other functions. So that's where life gets super easy, because whatever criterion I want to use, I can change it on one location and it will automatically compete all the rest. I know this is now a little much, I'm well aware, but follow along, rewatch the recording and think of examples that you have utilized in your life. Maybe have you used Excel at one point, and maybe this would have been helpful. I almost guarantee you will come across examples in your life or use cases in your life, but this may be helpful. I'd be surprised if not. Okay, so this is this. What else can we do? Well, I guess that was kind of good. Okay. So this is the discretization of a continuous variable. So you have a ratio variable and you make it discrete. You create an additional variable where you basically transform the information from your ratio variable into a discrete variable. In the particular case of 0 and 1s, it's a so-called binary or dichotomized variable. Dichotomous variables are basically where you only have two possibilities of entries. So you make it a discrete variable, you're assigning a value according to the ratio variable. Any questions on that? I know it's a little much and maybe it was a little fast, but it's like, this is along these lines to kind of like introduce you to the line of thinking when it comes to data processing. Good. Okay. Quantifying observations, use of data, and there's this floating panel again. So gone. So now we have pretty much the next level to discuss. When you are conducting research and you think of your operational variables, so these are the variables that basically determine what you are studying. You're asking a research question and you want to understand, based on the data that I'm collecting, how can I answer this research question? You will need 3 variables, or you will need more than 3, but basically you need 2 as the most important, and then you need to think of the third ones, which is usually not just one, that's usually like more. But basically you will always have a dependent variable. The dependent variable is basically your outcome variable. So that's the variable that you actually measure and that you're really interested in. So this dependent variable is, in the case of our Stroop test, it's the time, right? And this dependent variable is dependent and determined by the independent variable. So what's the independent variable in our case? It's the actual phase of that test, whether you do congruent or incongruent. This is your independent variable. And this determines the magnitude of your dependent variable. And then you have, lastly, you have the confounders. And the confounders are usually manifold, and you have your usual suspects that you use to control your analyses. Age, sex, race, ethnicity, you name it, right? It's like you use standard confounders that you assume may have some influence. And in the context of our Stroop test, it could, for example, be, did the individual have a stroke or not? So if you find a large difference between congruent and incongruent, it may be explained that you asked 10 students and 14 stroke patients in a stroke ward in a hospital. That would be a confounder. There's always a selection bias, but let's stick with confounders for now. It becomes more complex the deeper you get, but it's like this would be potentially confounded. And it confounds your other measures. So any questions on that? Next, reliability and validity. So reliable and valid. So in a perfect world, you have a reliable and valid measure. You measure something with a perfect accuracy, and you measure it today and tomorrow, it's the same result. And it's equally valid each time you measure it. It's almost guaranteed that will not be the case. accuracy and the associated reliability and validity, it fills book, and there are reference methods that are somewhat valid. For example, if you think of weight, did you know that the definition of a weight when you step on a scale is basically calibrated towards a weight that is basically it's locked and stored in Paris. That is the weight. This is 1 kilo, and everything evolves around that weight. That is one defined kilogram, and this kilogram is basically hermetically isolated from the environment. It's at stable temperature. That this kilogram is never changing. So that's the source of all weights ever measured on planet Earth. So now you basically have replicas of that with the exact same measure, same density of the iron. I think it's steel, I forget. But basically, so you reference this weight, and then every scale on planet Earth is calibrating according to that measure, that source measure. Same with height. So everything, the validity of a measure is dependent on the reference value and then on the method per se. How reliable can it actually measure, and how well is it actually to measure what it's supposed to be measuring? And the reliability of a measure depends then on the method per se. How good is that measure actually from one day to another? How much can it change from one day to another, and why would it change? It's like when it comes to measuring tapes. Measuring tapes have their own biases, how you apply it, and like what's the reference point? Are you measuring from there to there, from there to there? If I measure it, it may be different when you measure it. So they are into observer variability. So there are like a million things that you have to take into account, right? So, but a reliable measure is consistent from one day to another. A valid measure is measuring what it's promising to measure. Valid and reliable, particularly when it comes to psychological surveys, the distinction between reliability and validity is particularly important, because if you have a survey that quantifies happiness, depression, quality of life, general health perception, or whatever it measures, how do you know it really measures what it's supposed to be measuring? And how do you know that the individual is not just checking any box? So you don't know these things. And there's statistical methods to actually test this internal consistency, whether these answers, these responses of the individual do really measure what it's supposed to be measuring. But we'll talk about this more in one of the later classes. I think it's chapter 16, but more about that then. Okay, so but basically reliability and validity, repeatability, and the accuracy of the measurement. The perfect variable would be reliable and valid, clearly. So there are tests out there, and I used a different example, but an example that Nolan and Heinzen want you to know is the so-called Rorschach inkblot test, and I showed it the other class before. I am not qualified to say anything about it, but it's kind of suspect to me. So this is the Rorschach inkblot test. It's like this somewhat abstract figure, which you would give your subject, your test subject, and you would have the subject interpret that picture. And based on the interpretation, you would diagnose personalities and personality disorders. That's all I know about it, and I'm not going to talk more about it, but read up on it. It's interesting. So to what extent this is reliable or not reliable, again, I'm not qualified to talk about it, but it kind of has an aura of being of debatable reliability and validity, and so it was discussed in the literature and amongst the psychology community. So it is a questionable reliability, and the validity of the information it produces makes it very difficult to interpret, because the interpretations, I don't know how they're interpreting it, so it's been debated. So that is an example for a debatably reliable and valid measure for your input test. Good. But what you really want to do, you want to express and formulate hypotheses. You have a research question and you're interested in a particular research question. You basically take this research question and you think of how you want to study that. And then you basically formulate hypotheses that will allow you to use statistical methods to test these hypotheses. And that is a process that is called operationalization of variables, of data. As an example, you're interested whether the blood pressure is affected by diabetes. So one way to look at this is you take data of 30 individuals, 15 of them diabetic, 15 of them non-diabetics. One way to look at this is you're measuring blood pressure of all your 30 subjects, and you compare them between the diabetics and the non-diabetics. You see a difference? Maybe there's something in there. The hypothesis that you're basically developing based on that is that I assume there could be differences. And then you basically go stepwise. You say, okay, so I develop now first a null hypothesis, and then in the next step, a research or alternative hypothesis. Under the null hypothesis, I assume that there's no difference in blood pressure between those two populations, between those two sample populations, which basically the dependent variable here would be blood pressure. The independent variable would be diabetes status, diabetic or non-diabetic. These are the two levels of the independent variable that are determining the dependent variable of blood pressure. So now the null hypothesis is that there's no difference. So that's like there's no difference between diabetics and non-diabetics in terms of their blood pressure. The alternative hypothesis is there is a difference between the blood pressure of diabetics compared to that of non-diabetics. So what I do then in hypothesis testing with statistical methods, I assume there's a difference and I calculate the probability of me assuming that there is a quote unquote significant difference between two groups. And I quantify the probability of diagnosing a difference between those two groups being wrong. That is the quote unquote p-value, the often quoted p-value. This is the probability of, if I say there's a difference, how likely am I wrong? That's the probability I'm calculating. And we will get to that later on. So you assume under the null hypothesis there's no difference, then you take the alternative hypothesis and you quantify the probability that the alternative hypothesis is wrong. That's hypothesis testing. So the most important thing when it comes to hypothesis testing is to understand your variables and to operationalize them. When you operationalize them, you are defining your variables into a framework that basically allows you to frame the hypothesis in terms of variables, in terms of independent and dependent variable. Sounds now very fancy, but what it essentially is I have a research question. And I'm thinking of an independent variable and a dependent variable, and I'm trying to explain the dependent variable based on the independent variable. So if my research question is, are pet owners happier people? I can say my dependent variable is the level of happiness, quantified as said before on the scale from 1 to 5. Whereas my independent variable is, does the individual have a pet or not? Secondly, we have the level of cigarette smoking. is the individual a smoker and how much does he smoke? And the independent variable would be amount of willpower. So are people that are smoking showing a lower degree of willpower? So you would try to operationalize level of cigarette smoking, whether the individual smokes 2 packs, 1 pack, formerly smoker, never smoker. You categorize that and you basically associate that with the amount of willpower. Or how caring, so does social media use determine whether an individual is caring for other people? So the dependent variable would be how caring are people, and the independent variable would be social media use. So this is the operationalization. Any questions on that? Please kind of work on really, how should I say, memorizing these approaches and these concepts, because these are questions that you will be facing on the exams. And these are very central to essentially the topic at hand. Then you have so-called operational studies. Operational studies are basically correlational studies are basically studies or analytic approaches that are associating 2 or more variables. And this is a correlation of 2 variables. So you have here health behavior and the use of wellness programs. So you're saying here that the health behavior associates with the use of wellness program. So yeah, so this is a correlational study that basically is depicted here with a so-called scatter plot. And the characteristic of such a scatter plot is that each individual point here is one individual. So each individual has basically a certain level of health behavior and a certain level of wellness use of wellness program. And this is reflected here in the scatter plot. Yeah, and this is one way to quantify that. There are different ways to quantify that, and we will do that in chapter 15 and 16, because in essence, you can quantify the correlation between these 2 variables with the so-called correlation coefficient. And secondly, you can develop a model, a regression model that allows you to quantify the health behavior of an individual that is using a wellness program to a certain extent. Another way to analyze data, and this is now stepping away from the correlational design, which is observational in nature in most cases or many cases, is an experimental design. So an experimental design is basically where you're placing an intervention on an individual that participates in your study. So in principle, there's observational research design and there's experimental research design. Observational research design is basically where you're just observing people. You're following people and you're observing them without doing anything. And you may create 2 groups that you're following, but basically that's something the individual has been assigned to without actually actively doing something. It could be smoker versus non-smoker. It could be, so this is also of note, you couldn't really do a randomized study. You couldn't randomly assign somebody to become a smoker, right? So it's a little tricky. But so experimental studies, basically, you will have by design individuals assigned to either group. So you have, in most cases, it's usually a control group, which doesn't get the intervention, and an intervention group in which you have an intervention. Then you can have more intervention group. You can have intervention group with 1 medication, another intervention group with another medication. So there are different ways to deal with that. But basically, the independent variable is here the group assignment. So the different levels of the independent variable is the assignment to control group, intervention 1, intervention 2 group. These levels determine these levels and determine then the dependent variable, which is blood pressure, health behavior, you name it. Why do you need to randomly assign them? Because each individual will then have an equal probability to be assigned to either group. Why is that important? Because if you would allow them to self-select them into a group, let's assume this example. So we have a corporation which is concerned about the health behaviors of the employees, and they want to create a wellness program. So they are randomized, they are assigning people, and they allow for self-selection of people into groups that have access to a wellness program and to not have access to a wellness program. If they are self-selecting, you will have, in the end of the day, in your dependent variable, likely not much, a force difference between these two groups, because these individuals that will actively go into a wellness program will automatically be A, those that are healthy, B, those that hold a strong interest in being healthy, and these will be substantially different. Both groups will be substantially different from the group that has no interest in health behavior at all and basically smokes 2 packs of cigarettes and sits on the couch eating potato chips. So it's 2 different groups. These are different groups, right? And if they're self-selecting, the difference will be large, but you cannot make a causal statement. The only way you can make a causal statement, and this is what's meant here, you control for confounding variables because you are able to make causal statements. You can say, my wellness program did affect health behavior. If each individual was randomized to be either part of the wellness program or not be part of the wellness program. And this is why randomization is important. It's the only way in research how you can make, how you can draw inferences and make causal statements. Otherwise, you cannot. In the very same topic, if you have a randomized controlled trials, you have a between groups design. You basically have different people in different groups. So a randomized controlled trial is between groups design because you're comparing one group versus another group. So this is a between groups design. You're comparing those groups and the outcomes. If you have a within groups design, that's more like where you think, okay, so I'm observing an individual over a year. I make 3, 4 different assessments. I've repeated the assessments, and then I correlate the dynamic of these individuals in a within groups analysis. So correlational analysis are classically within groups analyses. But you can also use fancier methods to basically just do between groups design, but you have repeated measures within groups, but that's too much for now, but we get there. So, but basically keep in mind, between groups design, you're basically comparing two groups. Within groups design, you compare the individual within one group. Last, introduction to data ethics. So data ethics is basically something that is of great importance because essentially the number of examples where the ethics in research have been violated, unfortunately, are ample. There have been numerous occurrences where this has happened. And those of you who do some research, you will likely have to do the so-called city training. And this training basically guides you through the set of principles that is mentioned here, and will also give you literature, and that there's also literature that you can find in that regard, where these principles of ethics have been violated in absolutely terrible way and fashion. And so basically, based on that, there were principles developed that allowed to do research in an ethical way, that basically entail research design, data collection, statistical analysis, interpretation analysis, and the reporting of outcomes. And these ethics are usually quite closely monitored. You have, for example, if you do prospective design, randomized studies that basically study human subjects, so human subject research. These protocols will need to be subject of a so-called review by an institutional review board, which is usually also labeled in some countries, it's called an ethics commission. So it basically, it is a board of people that will review the protocols that are being conducted, and they will basically give feedback on whether any ethical principle was violated, and they will basically analyze the research approach that you're proposing in very much detail. You also will need to give progress reports to the RB on whether there were safety events or adverse events that kind of shared a little bit of doubts on the safety of the intervention. You will also, in addition, you will need to register your research beforehand, before you even start collecting data. You will need to register your data, and there are governmental websites and institutions where you can register your data. And you can basically, you register your data and you transparently show that the research that you're doing, you will update this, and you're very transparent about it. And last but not least, there are also guidelines nowadays how you have to report outcomes, and you have to report outcomes that they're really presenting the data in a way and fashion that is transparent, informing the community, has not violated any reporting or statistical principles, and is basically sound research, and your conclusions are based on solid grounds. So these are data ethics. And lastly, there's open science. And open science is getting stronger and stronger. You feel it whenever you write a manuscript, whenever you have in the process of having the manuscript reviewed and on the review. So open science is encouraging collaboration, which includes the sharing of methodologies used, the sharing of code. So when you, for example, you code R for an analysis, many journals will ask you,
could you try again?
I'm not trying again. So you're sharing your code, and you make it accessible to the community, to your readers, that they can study what steps did I take in analyzing my data. This goes even as far that some journals nowadays actually ask you to share your data. So not only the analysis and not only the codes, but also the data per se. And that's actually, you will find, so those of you that are analytically inclined and want to go further, is like there are a couple of journals where you really get the data to download directly from the website, and you can do your own analysis. You can replicate the exact same findings the authors have presented in their paper. And that's actually, so those of you that go further, it's like I've done that for many classes. I've taught many classes basically where this was done. So So it's a nice exercise. It's a very nice exercise, and it's a very live example where you really can replicate the findings of an author of a paper that you've read. Lastly, all of this basically leads to recreation of findings, and then also kind of a crowdsourcing principle that you have other people looking at your data and basically find a new angle to your data that allow for new insights. So, and that's really open science, which is fostering more collaboration, more transparency. Good. Any questions on any of this? No? All right. Then there are a couple of issues that are very inherent to psychological science. There are data-related problems, which are replication failures. For whatever reasons, the studies will not be possible to replicate. That could be for various reasons, could be different sampling, could be a different sample that is being studied, could be kind of a effect of a period, of a mindset shift, that some certain surveys only work in some certain periods of time, and then they basically are not resulting in useful information. Then you also have problems with data collection, which comes back to sampling. So, and this is unfortunately, and we will talk about this in more detail when we come to sampling. So one of the problems there is that many surveys have been conducted in what is called a convenient sample. And convenient sample is just like the name implies, it's just much more convenient. And so the problem there is really that you get a biased result. If you just take a convenient sample and you want to quantify the happiness level in your class, this may not be representative to the entire university. Or if you do it in the entire university, this may not be representative to New York City. If you have a survey for New York City, this may not be representative for the US population, et cetera, et cetera. Data collection as a next problem is like you have somebody filling this out in a very short time. Whatever they're filling out, this may not be really reliable and valid what they're actually filling out. They may not understand the question. Next problem. You have basically with every survey that you conduct, you need to make sure that this survey is actually validated in that population you're administering it, which is a huge issue with international studies. So usually you have at the beginning of each study, you first need to go into the literature and find out whether this study is actually validated in whatever language you could think of. Like, I want to do a study in China, it's like I need to make sure I have a tool that is actually validated in Chinese, right? Or in that language. In China, you have, I don't know how many different sub-languages and dialects that are spoken. So it becomes really complicated. Then you also have to see about data collection and the accuracy of these responses, whether this essentially is also to be used in the cultural context. So there are so many different dimensions that you have to take into account. It's really, it's very complicated. Old-fashioned statistics, I guess this is not the most, well, maybe it's still a problem. So old-fashioned statistics is basically focused only on hypothesis testing, which is black and white, yes or no. The argument that Nolan and Heinzen want to do now, that here's now the new statistics that are on the format. And this is what Nolan and Heinzen are discussing in chapter 8. When we talk about confidence intervals and report your data, also reporting the variability. So that's this. And then lastly, and this is where we're getting into data ethics in more detail. And I talked briefly about pre-registration. So this is really, we actually have quite a bit of time. I can show you this. So you have, for example, if you're interested in, these things in more detail, you can, for example, if you want to know what literature has been published, you go on a site called PubMed, and you can basically find every research that you want to do. So if you want to know something about chronic kidney disease, you can find easily every entry that deals with chronic kidney disease. So you can on PubMed, you can actually scout out the currently available literature on a particular topic. Secondly, you can also do, so that's PubMed. That's the literature aspect of it. So you will have here the authors, you will have the journal, you will have the issue of the journal, you will have an abstract. Sometimes you can even click and get the full text. So this is where you get literature from. Secondly, you also have a very interesting site. So it's called clinicaltrials.gov. Clinicaltrials.gov is basically giving you a characterization of all research that is currently being conducted and had been conducted in the past. So this is pre-registration. So you look for whatever condition you're interested in. You look for chronic kidney disease. Here we go. Chronic kidney disease, and here you get a list of all studies that are currently conducted with chronic kidney disease, and you see whether it's completed or it's still recruiting. So that's clinicaltrials.gov. And this is pre-registration. pre-registration to go and tell the community, I want to do this research. I got an IRB, and you basically list the IRB and you say like, okay, so this is my hypothesis. I'm doing the study. I'm recruiting 50 patients and I'm starting now. And then down the road, you're completing the study and then you publish it and then you add your respective publication to your registration. And you're doing that to be transparent about your research, and you show the community that your research has been brought to fruition, and you have transparently studied what you said you would study, and you have followed the hypothesis. You have not been on a fishing expedition. And the fishing expedition is basically this. So this is harking. So I haven't heard the term before I started teaching this class, but I find it a very, very interesting term. So we refer to this in my world as a fishing expedition, and it's pretty much the same. Harking is hypothesizing after the research results are known. So when you basically know there's a difference in blood pressure between diabetics and non-diabetics, and you've seen that pattern as like by the eye, you looked at the data and you know in a way already, and you're writing your manuscript around exactly that. You're doing more and more analysis, then this goes in the realm of harking. So it's debatable, because you should develop your hypothesis and you should have your research questions straight by the time you start your research. So you should do hypothesis-driven research and not just choose a self-fulfilling prophecy. So that's what harking is. Good. And also, if you change your hypothesis to match what subset analysis may find, you also increase the risk of a type 1 error. Okay, that comes later, but it's basically where you see a research result just by pure chance. So you shouldn't go this pathway. Good. So it's 7:13. We have 7 minutes left. That gives us a couple of minutes for R. So please open your R Studio. Download from the module the R code, module 2, Stroop data. So what the Stroop data set is exactly the Excel spreadsheet. Please comment, put a hashtag in front of line 7. So that's the hashtag in a code like that. As soon as you put a hashtag in front of your line, this will basically turn to green. That means it's commented out and cannot be used and will not be used by R for any analysis. You're doing that, so you use this commenting either if you have an inactive command that you don't need and you don't want to in any way interfere with the flow of your code, then you comment out, or you use commenting to kind of give yourself a couple of tips, give your future self a couple of tips of, why did I essentially write that line of code? What was my rationale in writing this line of code? What was that function about? So you're supporting yourself when you go and revisit that code 3 years later. You will not remember. So when you, for example, you write a paper and you start writing in code, you will end at the end of the day, like a good solid paper, you're writing 3,000 to 4,000 lines of code. So that's 4,000 lines of code. And if you don't have a structure in there and you don't have comments of what each respective part is, good luck if you send it to a journal and the reviewer comes back to you, yeah, there's this figure and I really would like to see, I don't know, I want the legend differently. Good luck finding that line of code. So it's you're helping yourself in a way by commenting and walking yourself through the process. So once you go back 3 years later or a year later, it will help you moving forward. So this is why you do commenting. So line 2, if you go on line 2 and you press Control and Enter, you will create a data frame that is here on the right top side, which is basically a DF, which contains exactly that Stroop data we've just discussed before. So we have the ID, we have congruent and incongruent. Yes, it's on Canvas. It's in the module. It's the file Stroop module 2 stroopdata.r. So if you download it, and please open it from R Studio. So open R Studio, go on File and Open, and then find it where you downloaded it. Okay, so line 2 is that. Line 11, with the ls function, you are displaying what variables are contained in my data frame, which is a congruent ID and incongruent. If I go on line 14, here I'm basically building histograms, which we don't need to do, but we can do it. So this is basically a so-called histogram, which we're discussing in chapter 3. A histogram is basically nothing else but on the x-axis, it has a certain entry. So this is a certain amount of time it has taken to complete the Stroop test, and it gives you a frequency within that, on that value. We talk about this next class on frequency distributions. The histogram is basically a visual depiction of such a frequency distribution. Then we have summary. With summary, you're basically building here a mean, median, and the interquartile range. We talk about this in chapter 3. Comes in more detail then, and you can easily address these variables. So df is the entire data frame. So if you do df, it will show you the entire data frame. If you do df $ and the variables, you basically only get the respective variable displayed. If you want to do the same exercise that we did in Excel, you can assign the number 15 to a little object or variable that is called A. If you press Control and Enter, A will from then on contain the number 15. If you're now using the length function basically takes one of these variables and counts this variable. So if you do length df incongruent, it gives you the length. So that's 24, right? It's counting down how many entries are there. And if I say congruent, but only take those congruents where my congruent is greater than A, then it will only give you those that are greater than 15. So it will only give you those that are greater than A, which is 15. If I do the same now as I did in Excel and I say A equals 10, and I run the same code, it gives me the 20 that we quantified in the Excel spreadsheet. So that's how you do the same exercise that you did in Excel in R with one line of code. And that's the beauty of it. And if you remember soft coding and hard coding, this is soft coding. All right, any questions? I know it was a lot, but you have the video to rewatch it. If you want to play around in an hour, please do. Let me know if any questions. That's all I have for today. Have a nice evening, and I'll see you on Wednesday. Bye-bye. Thank you.